Hi everybody and welcome to Unit 7. In Unit 7 we are going to focus on chemical bonding and then talk about the importance of water. All right, so let's just start out talking about why do atoms combine to form compounds? Well, not all atoms do. Most noble gases actually don't form compounds, at least they don't very easily. And that's because they have that full outer energy level, those S and P sublevels. So we say they have their full octet, except for helium because it only wants 2. All right, so they're stable and you can kind of think of them as very fulfilled. They're happy. All other atoms, remember, want to do something to get that octet. And the way they do this is that they bond with other atoms. There's 3 general types of bonds. All right, there are ionic bonds, covalent bonds, and then finally metallic bonds. Now, we typically say, and we did this with naming, you know it's ionic if it's a metal and a nonmetal. Covalent is 2 nonmetals. And then metallic is going to be 2 metals. That's just kind of the general form, but we're going to talk a little bit more about that in a couple minutes. All right, so let's talk about ionic bonds. And again, we are used to this. We have dealt with ionic compounds quite a bit. Ionic bonds involve the complete transfer of electrons from one atom to another. So sodium atom and the chlorine molecule, because it's diatomic, both of these, all right, are neutral. They do not have a charge. But what they will do in the presence of each other is sodium will lose an electron, those chlorides will gain them. They will become ions that have full charges, and then they end up becoming stuck together. And that is because of what we call electrostatic attraction. And that is the attraction between opposite charges. All right, after the transfer, both ions have complete outer shells and both have noble gas configurations. So they're nice and happy. Okay. Here is just a model of what sodium chloride, which is table salt, would look like. And something important to note here is that if you notice, it's not just a single sodium and a single chloride. All right, it becomes what we call a lattice, and it's a repeating pattern of chlorides to sodiums to chlorides. We say that this is NaCl because it is the ratio. You get 1 sodium for every 1 chloride. All right, and that's also why we call them formula units. We don't call them molecules, okay? All right, so let's talk about some characteristics of ionic compounds. All right, when you think of an ionic compound, thinking of table salt is a great idea. That's a great example of it, sodium chloride. All right, they are not made of individual molecules. All right, instead, they have that repeating pattern that we just talked about. This causes them to have high melting points. They tend to be brittle solids at room temperature, tend to be soluble in water, although we know not all of them are. They are good conductors of electricity, but only in their molten state. And the molten state is when they are actually melted, which is going to be really high temperatures. As we mentioned, they have high melting points. Or if they're dissolved in water. All right, when they're dissolved in water or they are aqueous, as we have talked about before, they're great conductors because they have those charged particles. They'll have the sodium ion, if we're talking about sodium chloride, and that chloride ion. But if you leave them just in their solid state, like here we have with our table salt, sodium chloride, this is some copper 2 sulfate. All right, if you just leave them in the solid state, they actually do not conduct electricity well. They need to be in a situation where those ions are kind of open for that electron flow. All right, let's move on to talk about covalent compounds. These are compounds that are formed when nonmetals share electrons, all right? This gives us individual molecules. The covalent bonds themselves are strong, what holds the atoms together. But what holds one molecule to another molecule, some are strong and some are weak. And this is important because it's going to give us some really large variation in its characteristics. You're going to notice as we go over these, they're not very helpful. In general, covalent compounds have low melting points, all right? They can be gases, liquids, or solids at room temperature. Covalent compounds range from things like oxygen gas, all right, nitrogen gas, things like water, ranging all the way up to things like sugars and things like plastics, all right? Those are all considered covalent compounds. Some are soluble, okay, like sugar. Some are insoluble, like oils. All right, we're going to talk more about that later. This is an important one, they are poor conductors of electricity. There are no charged particles in these covalent compounds to carry electrons. So they are not good conductors of electricity at all. All right. Now, the last thing, as far as all of these terms on this front sheet of your notes, before we get to working on something else, how can we predict whether you're going to form an ionic or a covalent compound? In general, as I mentioned before, metals, if you have a metal and a nonmetal, it's ionic. If you have two nonmetals, it's covalent. But there is something a little bit more to it. There is something that is known as electronegativity. Electronegativity is the relative tendency for an atom to attract a shared pair of electrons when it is bonded to another atom. The general trend, all right, for electronegativity is that it increases across the period. So as you move from left to right, electronegativity gets larger. All right, and it decreases as you go from top to bottom. Now, there is an exception to this. The noble gases, remember, they don't want electrons. They're happy the way they are. So really, we don't even discuss those when it comes to electronegativity. All right, let me show you just a visual here. Hopefully this comes up. Here we go. So here's a table of electronegativities. If you notice, as I mentioned, these noble gases, we don't even discuss them, okay? Electronegativities are numerical values. These are always something you would look up, all right? You would not actually have to remember these at all. You should remember the trend. We're gonna get larger as we move from left to right, all right? And we get smaller as we move down the group. This leads us to fluorine having our highest electronegativity, cesium having the lowest. Okay, all right, so let's get back to our notes. All right, so there we go. Now, there is something that is called an electronegativity difference, and this is used to predict bond type. All right, and simply if you would have those electronegativities, and I would give those values to you. All right, and here's what's kind of going on. If you would take the higher electronegativity, subtract from it the lower, and that gives you electronegativity difference. Just going to give you a number. All right. If you get between 0 and 0.4, we consider that a covalent bond. All right. If you're between 0.4 and 1, it's still covalent, but that's going to lead us to, it's being called slightly polar, and we're going to talk more about that later. Let's get down here. If our difference is basically 2 or higher, we consider that an ionic compound. We can use that little shortcut for metals and nonmetals and two nonmetals. For our purposes, certainly, if you move on in chemistry, you will deal a lot more with these electronegativity differences. All right, so we're going to continue and talk a little bit more about covalent compounds. And actually, we are going to be doing something that are called Lewis dot structures. And these are models to show what's going on within the actual molecule. All right. When you do a Lewis dot structure, you are dealing with only the valence, all right, electrons of the atom. Okay. And just as a reminder, okay, your valence electrons are periodic properties. Okay. So based on what group you're in, that's how many valence electrons you have. The valence electrons are the outer electrons, the electrons that are actually involved in bonding. So group 1 has 1 valence electron. Group 2 has 2. Okay. Group 13, 3. 14, 4. You can see the pattern here. 15, 5. 16 has 6. And group 17 has 7. Now, why did we skip these groups in the middle? All right, those are your transition metals. They're really not going to be involved in covalent bonding at all for our purposes. All right, so we don't have to worry about those. For the most part, we're going to be focused down here. All right, and then certainly with hydrogen. So with hydrogen and our nonmetals when it comes to these Lewis dot structures. Okay, so how do you actually write out Lewis dot structures? So it is this way. Okay, so steps in writing Lewis dot structures for covalent compounds. You are going to look at your compound and you are going to count up the total number of valence electrons. You're going to choose the central atom. This is going to be either the first one written, or if there's only one single atom, it's going to be that single atom. You're going to place all of the other atoms around that central atom. you're going to give all atoms 8 electrons, okay, unless it's hydrogen. Hydrogen only wants 2. Then you're going to check to see if your number of dots equals the available number of electrons. So it's always nice to have a check in there. All right. So let's look at 2 examples. Okay. Our first example is the compound CH4. CH4 is called methane. It's an organic compound, and we haven't done the naming for that yet. All right. First thing is we're going to count up the total number of valence. So I look here for carbon. Carbon's in group 14. Group 14 has 4 valence electrons. All right, so that's a total of 4. Hydrogen is group 1. I know on this periodic table you see that it's in both places. Please realize hydrogen just has 1 valence electron. All right, 1 valence electron, and so you have 4 of them. So that is a total of 4 from hydrogen. You're going to count that up, and that's going to give you 8 total electrons. Okay. Our next step, we're going to choose our central atom. Well, our central atom in this compound has to be carbon. We know this. First off, it's the first one written. Second, it's the only single atom you have. And finally, hydrogen can never be in the center. Okay, hydrogen will always be surrounding. So I am going to, write my central atom. I'm then going to place all of my other atoms around that central atom. So I have 4 hydrogens. I'm just going to choose that there's 4 sides. Don't worry about actual geometric shapes at this point. We are going to talk about that. I'm then going to place my dots around, okay? And dots need to stay in pairs because they represent electrons, and a pair of electrons is a single bond, all right? So you can write it like this, is considered a good Lewis dot structure, or you can write it with sticks, all right? And these sticks represent a bond, okay? So a single stick is what we call a single bond, but please remember that that is 2 electrons. So as I go to my final step, check to see if the number of dots equals your number of valence electrons. Well, that's easy to see here because I've actually used dots, and I have 2, 4, 6, 8. All right, and everything's happy. Carbon wants 8, all right, because that's what gives its full outer shell. Hydrogen just wants 2. We're all happy, we're good. Now, when you're using the sticks instead of the dots, you have to remember each stick is 2 electrons. So 2, 4, 6, 8. The 8 works out, and then we are good. All right, let's go on ahead and do another example. And this example is going to be water. So now with water, all right, remember we said hydrogen has 1 valence electron each. So that's 2 coming from the hydrogen. Oxygen is, we check our periodic table, is in group 16. So that means oxygen has 6 valence electrons. I'm going to add those up. I'm going to be dealing with 8. I choose my central atom. Remember, your central atom is either your only single, okay? Sometimes it's the first written. In water's case, it is not, because remember, hydrogen can never be in the center, okay? So we're going to go on ahead, and oxygen's going to go in the center. I'm just going to choose 2 sides for hydrogen to go on. All right, it doesn't matter. You could have written 1 above and 1 below. That doesn't make a difference. I'm going to now put my 8 dots. Remember, they always go in pairs to represent those bonds. Okay. All right, now I'm going to double check. Remember, I've used 2, 4, 6, 8. I had 8. Great. Everybody is happy and has what they need. I am here dealing with something a little bit different, and they are these dots here, all right? Those are what are known as lone pair electrons or unshared pairs. Means the same thing. Okay. They are pairs that are not bonded. Those are very common. They're very important. All right. And they're going to come up a lot. So we have bonds, which we consider shared pairs. And then we have unshared pairs. All right. Where there's nothing else connecting there. You can write this as a sticks as well. But please remember, unshared pairs have to be written as dots. We're going to find that this is actually not the proper way to write this, but we'll talk about that later when we talk about actual shape. All right, great. So let's go on ahead and see what happens when things don't kind of work out as perfectly as they did here. So sometimes you do not have enough available electrons to give you what is called a simple octet. And that's what we had last time, a simple octet. When this happens, you're going to have to use what are known as multiple bonds. So let's just remind ourselves a little bit. When you share one pair of electrons, all right, you have what is called a single bond. And that's what we had in our previous two examples. You can have situations where you are sharing two pairs of electrons, and we call that a double bond. All right. You can even have situations where you're sharing three pairs of electrons, and this, as you can probably guess, is a triple bond. All right. So let's see this in action. Okay, so let's get our first example. We're going to go through the same exact steps. So here's O2. Well, as we've said before, oxygen is in group 16. It has 6 valence. There's 2 of them, so we're dealing with 12 valence electrons. All right, so I'm just going to go ahead and do exactly what we did before. There's only 2 atoms in this molecule, so there is no center. They're just side by side. I'm going to go ahead and give them a bond here and then make them happy, right? Because oxygen needs a total of 8. That oxygen thinks it has 8. That oxygen thinks it has 8. Great. Now I'm going to check to see if I use the right number of electrons. I've used 2, 4, 6, 8, 10, 12, 14. This used 14 electrons. You don't have 14 electrons. You only have 12. Therefore, this cannot work. All right. When you find that you have used more electrons than you have, think double bond. All right, so now I'm going to rewrite this, oxygen and oxygen. Here we go. A double bond is sharing 2 pairs or 4 electrons. All right, and now each oxygen thinks it has that 4. So each needs 4 more, and we just kind of write them, trying to make things look as symmetrical as possible at this point. Let's check to see how many I used. I used 2, 4, 6, 8, 10, 12. Each oxygen thinks it has 8, 2, 4, 6, 8. 2, 4, 6, 8. So that's great. Again, I used 12. I had 12. That is the Lewis dot structure. Or you could certainly write it like this, with 2 lines as your double bond. And then we still write the dots for those unshared pairs. Okay. So either one of those would be acceptable. Why don't you go on ahead and pause and give nitrogen a try. All right, so for nitrogen, you should have found that you were dealing with a total of 10 valence electrons. Because nitrogen is in group 15, that's 5 valence electrons each, and there's 2. And we can kind of use the examples up above. We know if we had just given these 2, all right, nitrogen and a nitrogen, a single bond, I would have used 14. You don't have 14. Had I given the nitrogen's a double bond like oxygen, I would have used 12. Well, I don't have 12. So that means I'm going to use a triple bond. All right. So now with this bond, each nitrogen thinks it already has 6. So each just needs 2 more. Okay. This nitrogen now thinks it has 8. This thinks it has 8. Great. All right. I'm now going to count up 2, 4, 6, 8, 10. I have 10. That is my proper structure. Okay, or of course you could write it like this, and this would be perfectly acceptable as well. Okay, all right, so now I'd like you to pause the video and give this example, carbon dioxide, a try. All right, let's see a Lewis dot structure for that. All right, welcome back. So let's talk about carbon dioxide. All right, so carbon has 4 valence, oxygen has 6 each, which is 12. So you are dealing with a total of 16. As you should have already seen, all right, you should have, if you had gone ahead and just given everything single bonds, which you should to start out with, all right, given everything single bonds, and then carbon would have needed that, boop, 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 boop. It's more fun if you make sounds when you draw the dots. You would have found that you used 2, 4, 6, 8, 10, 12, 14, 16. All right. Let's do this again. You would have found that you used 8 and 8, which is 16, 17, 18, 19, 20. So that doesn't work. All right. So you end up finding out that what you need for this is actually 2 double bonds, one on each side. Okay. And then what's going to end up happening is this oxygen, each oxygen thinks it has 2, 4, so it needs 4 more. Boop, 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 boop. All right, so that actually works. And then we check to see how many we've used. We've used 2, 4, 6, 8, 10, 12, 14, 16. Great, so that works. You might have also found that this structure works. All right, and just give me a second to draw this one out. Okay, and then, so you might have found that because here I've used 2, 4, 6, 8, 10, 12, 14, 16. Everything has its octet, but this is actually not the right answer. All right, please remember you want to try and choose the most symmetrical molecule possible. All right, so this doesn't happen, so it does not occur. All right, so if you get in situations like this, always choose the more symmetrical. Okay. All right. Last thing we're going to talk about for today is doing a Lewis dot structure for a polyatomic ion, which you absolutely can do. Polyatomic ions are actually covalently bonded, but they have an overall charge, and that's why we deal with them in ionic compounds. But the polyatomic ion themselves is a covalent substance, so we do we can do Lewis dot structures for them. All right. So let us look at these. And there's only one adjustment we have to make. And that adjustment is if it is a negative ion, you're going to add however much that charge is to your total number of valence. If it's positive, you are going to subtract. So let's take a second and look at 2 examples. All right. So for ammonia, which ones am I doing first? Yeah, for ammonium. Okay. And it doesn't matter which one we do first. Okay. So for ammonium, nitrogen has 5, hydrogen has 1 each, so that's a total of 4. But then this is a positive charge, so we're going to actually subtract 1. So it's going to be 5 plus 4 is 9 minus 1, so you are dealing with a total of 8 electrons. All right, then I just follow through what I normally would. So nitrogen is going to be my central. I have 4 hydrogens around it. All right, going to put my single bonds there. And remember, each stick is 2 electrons. So 2, 4, 6, 8. Great, I have 8, fantastic. The only thing I have to remember to do, and this is the only kind of difference in the way these look, is I put brackets around this and I put the charge of the polyatomic ion on the outside. So this is the ammonium ion. All right, great. Then let's look at nitrate. So nitrate, again, nitrogen has 5, oxygen has 6 each, and there's 3 oxygens, so that's 18. And then this is a negative charge, so that means I'm going to add. If it is a negative charge, you add that charge. All right, so that gives me a total of 24 electrons. Nitrogen is going to be in the center, oxygen around it, and again, you can put them around however you'd like. Take a minute and pause and see which Lewis dot structure works. All right, welcome back. You should have found that you need a double bond, and it doesn't matter where that double bond goes. It could have gone here, here, or here. All right, and then this oxygen just needs 4. Nitrogen's fine, it doesn't need any because it has 2, 4, 6, 8. Okay, and then we do the rest. And if you're thinking to yourself, wait a second, where are you getting this double bond from? Remember, I tried it with just single bonds. And then I see if that works. And it doesn't work. It used up too many electrons. That's why I needed to choose to use a double bond. All right, great. So now how many electrons have I used? And you'll get faster and faster at this. This is 2, 4, 6, 8. So there's 8 over here. 2, 4, 6, 8. Great. And 2, 4, 6, 8. Fantastic. I've used 8 times 3, 24. So that's a check there. I have to remember this is a polyatomic ion. And I need to bracket it. And then you put the charge on the outside. All right. One last note, what is known as a resonance structure. It's one of 2 or more Lewis structures for a single molecule that cannot be represented accurately by one Lewis structure. What does that mean? All that means is sometimes you're going to get in situations like we were here with nitrate. There's a double bond here, but you could have put the double bond on this oxygen and it would have been just as accurate. or you could have chosen to put it there, and it would have been just as accurate. Anytime where you're choosing where the double bond goes, all right, that is considered a resonance structure. So if I ask you to identify a substance that has resonance structures, this would be one. Ammonium would not be one. There was no choice in where any of those bonds went. All right, we're going to be doing a lot of practice with this, so take care.